All right, welcome back to Mathematics of Data Models. This is lecture 12. Um, Today we're going to talk about concepts such as positive definiteness, pseudo inverse, regression. Now, this is a Northeastern University class, CS 2810, and I am Professor Wu. So, we talked about symmetric matrices where if you take the transpose, it's equivalent to itself. For example, over here, if you were to take the transpose, notice that they're exactly the same. Now, today, we're going to talk about this thing called positive definite matrix. So positive definite matrix, or PD, is a symmetric matrix where all the eigenvalues are strictly positive. Okay, strictly positive. Now, previously, you remember that if it's symmetric, it allows us to do this thing called eigendecomposition, where A could become V transpose sigma V. Okay, and now, right, if all the eigenvalues inside sigma are positive, then that's when it's positive definite matrix. If we know if all the values are positive, right, it immediately tells us that it has an inverse. And because of last class, we can see why. You can see that if all these values are positive, the inverse is just 1 over that. We learned this from the last class. And therefore, if it's all positive, then obviously, right, inverse must exist. And secondly, given any vector x, if you take x times a times x transpose, this value is always going to be greater than 0. Hence, positive definite matrix. Okay, so this is an important property of the positive definite matrix. Now, another one called positive semi-definite. So not definite, semi-definite, PSD, is also a symmetric matrix where all the eigenvalues are positive or 0. So in just positive definite matrix, it has to be positive. But semi-definite could be 0 as long as it's not negative, then it's a semi-definite. So the eigenvalues are either positive or 0. Now, the matrix in this case is not invertible, and it's therefore we can't have an A inverse. We can see this pretty obviously. If there are some zeros in the diagonal, obviously you can't have 1 divided by 0. Given any vector, right, x, then it's always going to be greater than or equal to 0. So that's the difference between positive definite and positive semi-definite. Semi allows the possibility for the value to be 0 and the diagonal to be 0. Okay, so positive definite, here's an example of that. All the eigenvalues are positive. It's invertible, means you can have A inverse, and symmetric. Okay, positive semi-definite, all the eigenvalue has to be at least 0 or greater, as opposed to here has to be non-zero and greater. It's not invertible, and it's symmetric still. Positive definite matrix are very nice and easy to deal with, but we don't always have it. PSD matrix are easy to obtain though. We went through the last class. If we have tall or fat or non-symmetric matrix, we can always basically turn them into a PSD matrix just by doing this or this, multiplying by transpose on either side. So for example, notice how this matrix here, right, A times A transpose, A times A transpose, it becomes symmetric. Not only is this symmetric, if you take the eigen decomposition of this, you will realize that it is also positive semi-definite because all the eigenvalues would be positive. Now, this is the underlying idea for SVD, which we're going to learn today. So previously, we learned essentially how do you turn a matrix into a symmetric matrix. But we realize when we perform this or this, not only are we creating a symmetric matrix, we're creating actually a positive semi-definite matrix. And today's topic is going to be called a singular value decomposition. And that's what we're going to be doing, where we start with a non-symmetric, non-square matrix, right? But we then, because we multiply by its transpose, it becomes PSD. And therefore, all the properties for eigen decomposition now becomes usable again. We need to deal with so this idea is actually very useful because we need to deal with inverse of tall matrices. Like often in actual engineering, we need to solve a linear system that looks like this. In this case, A is not invertible, right? In fact, chances are, if we let this be V1 and V2, the two columns, and this is Y, chances are, is not in the span of V1 and V2. Okay? So Y is not in the span of V1 and V2. So in order for us to solve this, like we previously had this equation. If we multiply by A inverse A inverse Y, in that case, that's equal to A inverse Y. So previously we could solve it this way. If the A inverse exists, but in this particular case, right, we know for a fact that it doesn't. Like this is not invertible because, well, it's not a square matrix. So this is where the concept of pseudo inverse comes in. Instead of regular inverse, right, which is A minus 1, I think pseudo inverse use this symbol, like a cross. In any case, the idea of a pseudo inverse is very easy. Since A inverse doesn't exist, well, we can check if A transpose A inverse exists. And since this is a PSD matrix, very often it will exist because it might be just a PS matrix. So if it exists, this implies that I could just multiply the inverse by this to give us identity. Therefore, we multiply both sides by A transpose. Once we multiply by A transpose, we multiply both sides by A transpose A inverse. And if the inverse exists, in that case, this right here is called a pseudo inverse, right? Because if you multiply this by A, like it's going to give you identity. Therefore, this right here is kind of like an inverse matrix. So if you were to multiply this by this, you're going to get identity. And therefore, X is just equal to this whole thing here. All right. So I told you previously, chances are if you have AX equals to Y, and A are just columns of V1, V2, X equals to Y. Very often, Y is not in the span of V1, V2. Therefore, V1, V2, this solution doesn't exist. When a solution doesn't exist, one thing you can do is to project Y onto V1 and V2. If you were to project Y onto V1 and V2, then whatever the result is, Y hat, is going to be in the span because you literally project it onto it. And then you can solve the rest. So what's happening if we go back to this equation here? What's happening is we're projecting Y onto the span, column span of A. And then we take the inverse. That's how we get the X value. So notice that if it doesn't span it, you're always going to have some error. So in this example here, let's say we got the solution after we solve this, X is equal to 1 and minus 1.5. And now, for this problem, where if we actually multiply AX, it's going to give us this, right? Remember, this was the problem we were trying to solve. Now that we solve for 1, for x through this equation here. We solve for x. We can now multiply x by the matrix. X multiplied by the matrix. And ideally, we would get this. But if this point is not in the span for the columns, then you're going to have some error. So let's see. We multiply this by this. This is our result. And notice that they're not the same. And in fact, we have quite a bit of errors because, well, this is the best approximation, but you're always going to have some errors. Now, this kind of problem is a very famous problem called the least squares. Okay? So here's the problem that we often need to solve. What's happening here is we want to find x1 and x2, but y is not in the span, and therefore you will need to essentially do a projection first. So we basically went through this whole process to show that if you project y onto the vectors of A, then you can multiply it by the inverse and get x back. So we take this. Let's see if we can calculate it. First, we do A transpose A. So we multiply A transpose by A. And then we need to take the inverse, A transpose A inverse. So remember, we're trying to solve this. So we're trying to get this inverse. And this inverse, we can just use the rule for the inverse of a 2 by 2 matrix. Okay? If we have the inverse of 2 by 2, this is our result. Now that we have A transpose A inverse, we have this. We just multiply by A transpose and Y. So we multiply by Y, A transpose and Y. And here's our solution, 1.30.8. Okay, now we plug it back in, 1.30.8, and see how well it did. It actually it did not bad. It's pretty close. 0.8 is approximation of 1. 2.1, approximation 2, 3.4, and 4.7. It's not bad. So this is our prediction. And what we could do is take our prediction and subtract the result, the true ground label. And then we find the norm of that gives us the final error. And this is called the mean square error. Okay, so the ability to solve ax equals to y with the previous example, where A is a total matrix, right? It's actually very, very well known, like leads to a very well known algorithm called regression. Now imagine that you have a set of points, right? You collect it. These are the set of points here, right? You have this set of points where you have some x and some y. Now, you have the data, but what you want to do is come up with a line that does a good job of fitting the data. And this line is essentially a function where you put x and it gives you some y value. So if you were to put this value in, it's going to say it should be over here. You put this one in, it's going to tell you it should be over here. Okay? So this function is essentially your model that allows you to predict future events. So once you have learned f of x, in the future, somebody tells you this person's input is x4. You can plug x4 in here, and then it'll tell you the predicted outcome. So there are many different kind of regression, right? There's the one that's more like just a line, which is called the linear regression. Or you can have something that curves, or you can have very complicated curves, right? So you pick the kind of line that you want to fit. Notice that by knowing the best function, you will be able to predict y at any given x. Given x, you will be able to predict the ideal y. The idea of regression is actually really simple, okay? So it's really simple. Let's say we have some data as x and y, just like we saw here. We have some data. Do I have some data here? No. All right, let's just say I have some data. Yeah, right here, x and y. We have some data, and we assume there's some function such that we plug x in, it's going to give us y. And the idea is that we want to find the f, the function, such that when we plug x in, we can get y back, or at least an approximation of y. So how do we find this function, right? Like if we have some input and these are the output, we want to find the function such that we put the input in and give us the output. If only we can find that function, then the problem would be solved. But it's really, really hard to find the function. So we're not really certain what the best function is. But what we normally do is we make some educated guess that it's some combination of bunch of functions. So we have f1, that's some function, f2, f3. So some combination of the weighted f1 plus weighted f2 plus weighted f3, that combination accumulates towards like the true function. And in this case, we don't know what A1, A2, A3 is. We don't know how heavy, how much weight we should put on each function, nor do we really know what the function is. So where did we go from here? Well, in regression, what we normally do is we make an educated guess for what F1, F2 is, okay? And then once we do that, we can solve this problem to get the ideal X. Okay, so for example, assume we have the following data. So if we had the ideal function, if we plug 0 in, it will give us 1. If we plug 1 in, it will give us 2. Plug 2 in, it will give us 3. Okay, so we have some data, and we want to find a function that maps x to y. Well, assuming we can make an assumption and say, let's just say we only have two functions, f1 and f2. Therefore, f of x is equal to a1 f1x, a2 f2x. And ideally, that's equal to y. So in this data set, there are 3 points, right? 3 points, which means that, well, if we plug point 1 into this function, that should give us y1. If we plug point 2 into this function, it should give us y2. Again, if we plug point 3 into this function, it gives us y3. So because we have 3 points, that actually give us 3 equations. And well, we know, right? If we know, we could just plug first point here, second point to here, and the third point to here. So we can now write this. We can now write this into a matrix form where we have F1, we plug 0 in, F2 plug 0 in, F1 again, plug 1 in, F2 plug 1 in. So basically I copy this over here. And I can pull alpha A1, A2 out is equal to 1, 2, 3. Okay, so this is equivalent to the form AX equals to Y, right? Depending how we pick F1 and F2, then you'll get a different algorithm. So we can now, there's an algorithm called linear regression. In linear regression, what you do is you pick F1 to be X and F2 to be 1. So no matter what you plug X into F2, your result is always 1. So that's linear regression. Now, if you pick F1, F2, F3, 3 functions, F1 is equal to X squared, F2 is X, X3 is 1, then what we're doing is we're solving another one called polynomial regression, right? So the idea, all of these goes from here. We're trying to find a function such that if we plug X in, it gives us Y. And since that we don't know we don't know what this function is, very often we make an educated guess that it's a linear combination of a bunch of functions. If it's a linear combination of a bunch of functions, right, that depends on how you pick function 1 and function 2. So let's say here, we pick function 1 as x, function 2, then that's one algorithm, which is called linear regression. If we pick x1 square, x2, f of x2 is just the function x, f of x3, right? In this case, we have a second order polynomial regression. So let's do this example with a linear regression. If you remember the linear regression, right, it's saying that f of x is equal to a1 f of x plus a2 f of x. Okay, so this function looks something like this. And this is just an assumption. Right? And in linear regression, we pick f of 1 as x and a1. And f2 is 1. 2 times 1, which is just a2. Okay. So now we now know that the equation that we think is happening is a1x plus a2. Right? So now if I were to plug here 4 points, we plug point 1 into the equation, point 2 into the equation, 3 and 4. We plug all these equations. Ideally, each one of them would allow us to predict the output y. So we end up getting, like, if we actually plug x1 in, then we're going to get 0, 1, 1, 1, 2, 1, 2, 1. Okay. After this, we can put it in the matrix form. Now that we're in the matrix form, then we can essentially solve this using the technique I told you previously, which was so let's call this a x equals to y, right? Therefore, the perfect x would be a transpose a inverse a transpose y. Therefore, if we want to find the function, we want to find a function such that allows us to take input this and output this. Input this, output this. Input this, output this. The perfect alpha 1, alpha 2 for the equation, for this equation, alpha 1, alpha 2, can be found using this. Okay? So the first thing we need to do is calculate the inverse. So we take x a times a transpose, and now we can calculate the inverse, which is right here. Now I taught you how to quickly calculate the inverse of a 2 by 2 matrix. So once you calculate the inverse, it should look something like this. And lastly, we multiply all the terms together. We take this, which is here, multiply by a transpose, and multiply by y. And the final result is right here. So that's what x is. Now, remember, the vector x is essentially equal to a1, a2. Okay, x is equal to a1, a2. And what was a1, a2? Well, it's part of a function, a1x plus a2. Okay, so we essentially now have discovered what the function is. Right? I wrote it here. So we know a1 times x, a2 times y is equal to y. So now these are the 4 points we have. And notice that after we come up with the best fit line, it looks like a reasonable fit. Okay? So I want you to know how to plot these results out yourself in MATLAB, or I mean in Python. So if you have these points, x points, 1, 2, 3, 4, 5, and y points. You can plot the points by writing PLT scatter. So this will allows you to plot these points out. Right? It plots these points out for you. Right? That's what this command does. And then what you can do is generate a linear space called linspace. So linspace, in this case, it generates number between 0 and 6. Oops. Yeah, it generates a number between 0 and 6, and you generate 100 of them. And then if you calculate the line, here's the line, then it will give you, for every single x value, it's going to give you the y value. So these are the x values for the line, and here are the y values of the line. And then you can write plot. So that plots out the blue line. The idea is that you have some data showing red. And what you want to do is find a function that does a good job of predicting the data or modeling the data. So once you do the modeling, if you can visualize this, you can see whether your data is reasonable. Does it look like it's a good fit of the data by doing this plot here? So you wanna make sure you understand what's going on here, because like ideally you will have the ability to plot your own data. Once you plot your own data, you will be able to come up with a function that does a good job of fitting. And then by plotting it out, you can convince yourself that you did a good job. So practice. Now, I want you to perform a second order polynomial regression, okay, with the following data. So here's the data. And you can plot this data out. You'll look something like this. And once you plot this data out, so actually, let's see, 0, 0, it'll be 1, 0, 2, 1, 3, 3, 3. Okay, so here, these are the points. So now you want to come up with an equation, right, that essentially can draw a line that does a good job of fitting them. Okay, so the assumption we're going to make is that the function is equal to some kind of a1 times x squared plus some kind of a2 times x. So we're going to assume this is a function, right? And these are the points. See if you can come up with the equation yourself using the closed form solution. Okay, so remember the steps. The first step is use this equation and then come up with 4 equations. So there are 4 points here, right? So for each one of these points, you plug in x. That should allows you to predict y. And by having these 4 equations, you should end up with ax equals to y. And then from there, you can solve x using the pseudo inverse, which is A transpose A inverse A transpose y. Now you get x, right, which is equal to A1, A2. And now you know the equation. Okay, give this a try. See if you can do it. Over here is the solution. So I basically give you a step-by-step process. Okay, so this was the equation I gave you. Ax equals to y. And you can find the optimal x with A transpose A inverse A transpose y. And notice that's exactly this equation. Okay, so you can solve it this way, which is the equation, or you can use the linear algebra library, which is least squares. You put the A, you put the y, and it solve for x for you automatically. It also gives you the error. Okay. Now, given this data that we had, so notice this is exactly the same. And remember when we solved it previously, the solution was 0.5 and negative 0.5, which is exactly what they got here. Okay? And the final equation is this. Let's try this again. So, oh yeah, this is the plot. Here we go. So here's the plot. You have 0, 0, 1, 0, 2, 1, and 3, 3. So now notice when you find the appropriate function, it actually does a really, really good job of predicting the points. So the two of the most basic regression methods. So I showed you, depending on your assumption, depending on how you pick F1, F2, you can have different algorithms, right? And the two of the most basic algorithm is first linear regression, which you assume that F1 is equal to X, F2 is equal to 1. So that's the assumption. And then resulting in functions that looks like this. Now, the other one, you assume that there are three functions, F1, F2, F3. F1 is X squared, F2 is X, X3 is equal to 1. Okay, so this right here is yet another assumption, and we give it a different name called polynomial regression. And it results in functions that look like this or this. Both cases, we solve them exactly the same way. We put it into AX equals to Y, and then we solve it. Final practice of the day. Well, given this data here, right, and we're going to assume that we're going to do a second order polynomial regression, which implies that we're going to assume F1 is equal to this, X squared, F2 is equal to X, F3 is equal to 1. So your goal is to identify the best fit function f of x. Okay? You can use Python to confirm your solution is correct. And you can use like this graphical calculator to plot the points. And you should see something that kind of looks like this, where you have a bunch of points and you try to find a good fit. Okay? Now, this is only 4 points. So it's fine. But if you in real life you end up doing millions of points. So you will need to essentially know how to do it in Python. Okay? So I think that is it. So I will see you guys in the next class.